All right, hey class, Mr. Pack here, and we're going to go through loads and load paths today, which is lesson 3.2.2. Picking up from last class where we started talking about structural forms, and generally we're going to look at some structural analysis today, and decided to do this more as a video recording just because there's going to be some parts that have to go through some calculations, kind of how to do different parts, and doing it in front of the whole class, sometimes it's really hard to see, so I think the video is going to be more helpful here. So we'll probably start off with this screen though. We'll do this part as a class, and then we'll pick up from here. Okay, so without further ado, let's get into it. Loads and load paths. All right, today we're going to cover structural design, design loads, different load types, combinations, load paths, and then we'll finally get into calculating beam loads. Alright, so when we talk about structural design, typically it's broken down into these 8 steps. First off, we obviously plan. How will the building be supported? Secondly, what kind of loads is it going to face? Third, we design for the different configuration and layouts. Fourth, we analyze the structural members, whether they're beams, girders, columns, things like that. Fifth, selecting the structural members that we're going to use. We'll evaluate that design, redesign if needed, and then design some of the detailing and the structural components. All right, so design loads. When we talk about this, we're saying what's the load that a structure is probably going to face. Oftentimes it will include the following: the dead load, which is just the weight of the structure itself. The live load, which would be things like people, equipment, what kind of things would be going into the building. Third, especially in the colder areas like here in Michigan, we'd have snow and ice load, what would be expected to be on the structure at any given day. Fourth, rain load, similarly. Fifth, flooding, if there's any potential for flooding, how that might affect the structure. Sixth, wind load. Seventh, earthquake, if you're in an area with lots of seismic activity. And then lastly, we have earth pressure load, which is kind of based on the soil and kind of how that surrounding area would affect the structure. Right, as mentioned, dead loads, you'll see that as the acronym DL, that's going to be fixed. That's often the weight of the building and some of the service equipment. So that could be, the HVAC unit, your air conditioning units, your heating units, things like that, as well as plumbing. Then there's the live loads, as mentioned before. This could be changing. Here in this factory, we see there'd be, equipment there. There's people, tables, furniture. All of that would be considered live load. It will change throughout the lifetime of the building, but you want to be able to at least predict or anticipate what kind of loads there would be. Okay, so this would be specified in building codes. So for example, if you're building a school compared to a warehouse, there would be different expectations for live load. All right, snow load, as mentioned, a lot of this is based on weather data, and so they'll depending on where you are, so location, what kind of wind factors, how the building importance, which is really saying what kind of people are going to be there. A school would maybe have a higher importance value than a warehouse, for example. And then finally, the roof slope also makes a difference. We've looked a little bit at this before, but a flat roof obviously will collect more snow than a sloped roof. Right, and here's where we do some calculations. So this equation looks maybe a little intimidating at first, but we'll see that a lot of these values are going to be given to you, or you're going to be looking up in a table, and then as you can see, you're just multiplying across. So design snow load calculation, we see that this PS stands for design snow load. So that's going to be what kind of load we expect in the snow based on these factors. One would be the roof slope. Second, exposure factor. Third is the thermal factor. Fourth, importance factor, which again is most of these first ones are based really on location. Importance factor is based on what type of building it is. And then lastly, ground snow load. This value you'll get based on the location. So you look at some weather data. I'll show you how to get that shortly. Okay, once you have all those numbers, you multiply them across. All right, so here's where we would find the ground snow load. So there's maps. These are oftentimes in the IBC or the International Building Code. So this is a snipping shot of this. So you can see, depending on where you're building, you'd look in that area. And then you'd be given a value. And this value is kind of what we are designing for. So that's kind of how much snow is typically seen in that area. Right, so for example, if we wanted to look at Springfield, Colorado, let's say we were building there, we'd find it on the map, and then that's what's marked here in the red dot, and we can see that that area has that number 15 marked right there. So this would say that this is 15 pounds per square foot is the average snowfall, and depending on that, that will give you, that would be your PG value, and then you can also see that that would also affect your design load. So if you have a value that's less than 20, in our case here 15 is less than 20, then our PS would be greater than the importance value times that PG. In other words, if it's larger than that, then we take that value times 20, whatever that value is. All right, so other loads that we often look for are lateral loads. These are kind of based on the environment around it, as mentioned before. So you have wind, earthquake, floods, earth pressure loads. So all those things will kind of affect the design as well. Okay, so wind, as you can see here, you'll see lateral loads, so moving side to side. You still get some downward and upward pressure on roofs, right? So this is kind of the same idea as how airplane works, creates lift when we have that air pressure difference. And then this could also affect the structure's stability. Okay, this is specified in building codes. We also have earthquake loads, so if you live in areas with high seismic activity, this is definitely something you have to think about. So building codes will help with that. Flood loads similarly, so they affect obviously large amounts of water, and the buildings will kind of determine where you need to build, how far above this elevation. There's maps for that as well. We'll dig a little bit more into that later, but a term you should be familiar with is base flood elevation, or BFE, and this is saying that there's a 1% chance that this flooding could happen above this level, and that's what we designed for, that 1% chance. Okay, there's another term that you should be familiar is dry flood proofing. This is meaning that this is designing so that it's just watertight to flood water. So if you live, close by a body of water or area that has lots of flooding, typically the builders would try to create a dry flood proofing type building, a structure. All right, and then final, soil pressure or earth pressure loads. This is the soil around it. We'll do a deeper dive into different types of soil later, and how different types of soil shift in different ways. And so, yeah, that's something you also have to think about. All right, load types. So there's two different types that we will typically address. One is uniformly distributed load. So for example here, the entire roof, we would anticipate that all the weight of the roof would be distributed evenly. So that would be uniformly distributed load. So we take the total weight of the roof and divide it by the area, and that would give you kind of the pressure. Meanwhile, concentrated load would be at a single point. So in this case, the car would represent a weight at one point on the roof. That would be a concentrated load. Okay. And typically when we talk about the overall load, we just add together all the totals. So the code itself will kind of tell you which ones to consider in your design. One of the more common ones would obviously be dead load and live load. Sometimes if you're in a high wind area, you'd have to account for the wind factor. If you have snow and earthquakes, for example, you might need to add those in your total load. For our examples, we'll often just kind of stick to dead and live load just to keep things simple. Right, so the design loads, building dead load is the only known one. That's the ones, based on the weight of the building, all the structures that would be added together. All the other forces will kind of vary depending on how long it is. So the snow, for example, will only be there for a certain amount of time, or even the people in it are going to come and go. And so those are some other things that you have to account for. Typically, the building you design for possible loads that may never occur, but you always want to overcompensate for it, make sure it's safe, so that if in case, even a building has, you change the building, more people end up going to the building, they can account for that load. Okay, so in class we might cover this, but I'm going to skip over this for now. All right, for getting a little more technical here, load path. So if you follow where a load goes, this is called tracing or chasing the load. So we're kind of seeing, all right, if there's weight coming down, how do we follow the structure such that all that weight or all that force ends up going to the ground? Okay, so the load path, every load will travel through the structural system until it goes to the soil. So again, we start at the top. If we have, for example, this concentrated load, it would fall along the beam here, go along these kind of girders, go down the column until it reaches back to the soil or the earth. Okay, we covered some of these structural elements in our last class, so I'm not going to spend a lot of time here, but obviously they all work together to get loads from wherever they start to the ground. So oftentimes they'll start from the roof, down the walls, towards whatever connecting beams, girders, columns, into the footing or the foundations, into the ground. Okay, so load chasing, so kind of following this load, oftentimes you'll follow it from slabs to beams to girders, then onto columns or walls, and they go down to the footing, finally to the earth below. So that's kind of what I just covered last slide. Okay, here's a few terms. Some of these we covered already. Beams and columns you should be familiar with. Footings we talked about also last semester. The one term maybe we didn't cover as much are girders. So girders are what kind of holds all the beams together. So they are the connecting point between beams is your girder. All right, now getting into some of the design work for beams. Right, so a design area, so let's say I was building out for a given, let's say, concrete slab here for the floor system that we're looking at. Maybe this is like a second floor plan, and we're figuring out what kind of beams we might need or how much weight we would need to support. Okay, so if this is the area we're looking at, we see I've got the four columns. It's a 3 span, so there's 4 beams total that it's going to cover, and then you got your girders along the side. All right, so one term that you're going to have to be able to solve for is your tributary area. Okay, the tributary area is kind of the area that a given beam is responsible for supporting. And typically all we look at is the distance between each beam and divide it in half. So in this case, we say that this beam between is 6 feet 8 inches, and it's going to be on each side. And so in total, it's going to be, for example, 3 feet 4 inches on this side, 3 feet 4 inches on this side. That would be your total tributary width on that side.
At this time, we are dismissing soft.
Okay, sorry about that. And then we multiply that by the beam length or the beam span. All right, so in this case, we see that the beam span is 18 feet. Tributary width is the 6 feet 8 inches. Again, the easiest way to do that is really just look at the distance between the beams, multiply them together to get your tributary area. Okay, so in this case, 6 feet 8 inches times the 18 feet. So our total tributary area for this beam would be 120 square feet. Okay, now calculating beam load. So in this case, we're going to use that tributary area in a second, but for now, we're going to take a look and see how is this going to be calculating for what kind of load that beam would take. So in our case, we're going to assume that this floor system has to support its own weight. The weight is 40 pounds per square feet. That's the dead load. And then in addition, we're expecting a live load of 100 pounds per square feet, or meaning like there'd be, people on it or maybe some equipment. So what is the uniform load applied to the beam? So we find the total floor load just by adding up the dead load and the live load. So 40 plus 100 gives us 140 pounds per square feet is the total. And then we're multiplying that by the tributary width, which is what we found in the last one, 6 feet 8 inches. Again, we want that all in feet, so 8 inches, 8 divided by 12 inches gives you in feet, so that would be 6.67 feet. Multiply those two numbers together, we get 934 pounds. This would be pounds per foot is what it would come out to. Okay, that's a P divided by F. All right, now girder loading, similar idea, we'll just do another practice. The girder, remember, is coming along here, and it supports multiple beams. Okay, and all that goes into a column. So we're kind of chasing the load here. Ultimately, we follow it down into a column. Same idea now. This column, we're kind of anticipating now, it's responsible for covering the distance in between each column. So in this case, since there's a total gap between the columns of 20 feet, cut that in half, there'll be 10 feet on this side, 10 feet on this side, so a total of 20 feet. Another way of easy way of thinking about it, distance between the columns is what we're going to multiply on that side, and then the distance between columns this way is 18. So in total, it'd be 20 times 18, giving me a tributary area of 360 square feet. All right, and same idea now, we're multiplying tributary area by the total floor load. So from our previous example, we say it's 40 plus 100, dead load plus live load, so 140. Multiply those two values together, 360 times 140 gives me 50,400 pounds. That's the load that would go towards the column. Okay, so next in your activity, which I'll do a separate video for, we'll see how we use these values to decide how big of a column we need or how big of a beam we need, and that will be your main activity for your assignment for today. Okay.